In this video, we're going to come back and talk a little bit more about how we can use a BJT as an amplifier. So this is a topic we're going to build a lot on in our next unit, but here we're just going to get sort of a taste of what the idea is. In order to do this, we're going to revisit a circuit that we had considered in a previous example. So that circuit is shown here. And we had found our voltage transfer characteristics. So this related our output voltage to our input voltage, and we also labeled our three different modes of operation. So now that we want to use this BJT as an amplifier though, we're going to make a slight adjustment to our circuit. We're going to take off this sort of constant input voltage and we're going to add some small signal AC voltage in series. So we still need to have that DC voltage to help us bias our circuit, but now we have this small time varying signal. So let's call this lowercase v, lowercase I, which is equal to 0.4 sine omega t, and that's in units of volts. So we see the 0.4 is a relatively small value compared to, for instance, our 10 volts supplying our collector side over here. And let's call this input voltage, our DC input voltage that's going to be biasing our transistor, VBB. So we can come down here to our diagram and we can change this from VI to VBB just to keep our notation consistent. Okay, so with this new circuit, there's sort of two things that we're going to be interested in. We're interested in what does our output voltage look like, and sort of before we get to that, we want to say where do we bias our BJT? So where to bias our BJT. And so again, we're going to talk about this first, and once we figure out where we want that to be biased, then we can come back and figure out what our output voltage is going to look like. So first of all, as I've said before several times, we know that if we're doing linear amplification, and most amplification that we're going to be looking at is going to be linear amplification, we want to be in the forward active mode. And so more specifically, what we're going to see is we have a preference as far as where do we want to be in this forward active mode. Well, we want to be in the middle of the active region. So middle of our active region. And again, we're going to see why that is here in a little bit. So basically what that amounts to is we look at this linear approximation here and we say, let's be right here, dead center. And so maybe I've not drawn that exactly right, but you get the idea. We want to be in the middle. So because we've already done some analysis for our DC circuit, and we'll come back to this idea later, but essentially if we want to do DC analysis, we can ignore this and just replace it by a short circuit. So we've done that and we found these two values here. So using that information, what we can do is we can say the necessary bias to put us right in the middle. So what basically we're saying, what is this middle value here? What does that correspond to? And ultimately, while I have my dashed lines, I'm going to go ahead and draw a line here because we're going to say what does that correspond to in terms of our output voltage. So our input voltage, or our VBB rather, is going to be the 6.09 minus 0.7 divided by 2, so that's sort of the midway distance between them. But we also have this offset of 0.7, so we have to add 0.7 to that, and we find that that is approximately 3.4 volts. So that would be 3.4 right there. Now, to find our corresponding output voltage, we would come back to our DC circuit. So again, we ignore this AC component, so we could short that out. We could do our analysis just like we did in the previous example. We find our base current by analyzing this base emitter loop. From our base current, we can find our collector current because we're in forward active mode, so IC equals beta IB. Once we know the collector current, we can figure out the voltage drop across the resistor. And then finally, we just subtract that voltage drop across the resistor from 10 volts to get our output voltage V out. So run through that maybe for practice, but ultimately what we'll end up getting is if we have a 3.4 volt input, our sort of average mean output there is going to be 5.09 volts. And so it turns out this point has a special name, so this is going to be called our Q point, and I know I've referenced that a few times before, so this is our quiescent point or our operating point. So our operating point isn't necessarily in the middle of the load line. Our operating point is going to be wherever we're operating at. or our Q point is going to be wherever we're operating it at. Ideally, we want it to be in the middle as I've shown it here. Okay, so now we've sort of answered this question of where do we bias the BJT. So we want to come back to our initial question of what does our output voltage look like? Well, we see that our input voltage has this time varying component, this VI equals 0.4 sine omega t. And so what that means is if we're again looking at, well, so let me maybe change our notation back here. So instead of a VBB, let's just say this is our overall input V sub I, and this is our overall output, which now has DC and AC components, V out. And so what this is going to look like is that our voltage on the input side is going to be varying between 3 and 3.8 because we have that 0.4 volt magnitude, which is being either subtracted or added to 3.4. And so again, we sort of, this is coming from the small signal AC part right here. So let me add sort of some more dashed lines here. And so we can look at this graphically and we can say, well, if our current is increasing, or sorry, our input voltage is increasing to 3.8, then based on this blue curve, which we got from our DC analysis previously, that means we're going to have some corresponding output voltage that looks like this. Similar thing for if we have our input voltage, again, this is the combined input voltage drop down to 3 from this curve, it's going to have some corresponding output voltage that looks like this. And so let me sort of maybe copy this and move this down so we have some more space to talk about this. But what we're going to see is, of course, if that input voltage is varying between those two, then our output voltage is also going to be varying in a sinusoidal manner. Okay, so if we come down here and we say, so this is our input voltage and here's sort of our middle point. So we have some input voltage that is varying like this over time. Then we're going to have some corresponding output voltage, which is going to be varying like this over time. And so notice that whenever, and so sorry, I've sort of drawn that backwards. So really it would be like this. So it looks the same, but basically we're saying this is going this way and this is going this way. The main sort of takeaway there is that when this is here, it corresponds to this point here. So the highest input voltage corresponds to the lowest output voltage. And so we could do our analysis, we could adjust some of the equations that we had written in the previous example, a previous video where we analyzed the DC part of this circuit, and we could come up with an equation that says our overall output voltage is equal to 11.27 repeating minus 1.81 repeating times our input voltage. And so again, this is if we're in the forward active mode. So we would have to assume we're not going into saturation or cutoff. And so we could use that equation to sort of verify that if we have 3 and 3.8 as sort of our two limits for our input voltage, then our output voltage is going to be varying between, on the lower end, 4.36 and 5.81. And again, keep in mind this plot isn't to scale. I'm just trying to give you a good idea of what sort of qualitatively is happening here. So an important thing with our amplifiers is, of course, our amplifier gain, so A sub V. So we can define that as the change in our output voltage with respect to change in our input voltage. And so if we take a derivative of this equation above, of course, we're just going to get negative 1.81 repeating. And again, that corresponds to these values. So if we have, a 0.4 volt swing, then we're going to have 1.81 times the 0.4 volt swing here. And so again, to be more specific, if we talk about our output peak to peak, so V output peak to peak is approximately 1.45 using those values above. And by definition, because we had that small signal input source, our input peak-to-peak voltage is 0.8 volts. And of course, we could sort of take the ratio of those, and we would see that that works out to be a magnitude of 1.81. And of course, the negative sign just comes in with the phase difference. So when this curve is increasing, this curve is decreasing. So that's where the negative sign comes in. So the question then becomes, what if our Q point moves too far to one end or the other? So what happens if Q point leaves the middle of the active region? And so what we're saying is basically we're taking this Q point right here. See if I can move this around. So we're taking this Q point here and yeah, it's not going to let me. So let's see if I can just get rid of that and let's put, okay, no, okay. Well, at any rate, we're saying if we move this Q point and we move it down to this instance, so maybe we're getting closer to the saturation, or maybe we move our Q point up here, closer to cutoff. And again, keep in mind this would correspond to changing the value of that VBB voltage. And what we would see is that as we shift sort of these dashed lines too close to saturation, at some point this rightmost red dashed line is going to be somewhere in this region, and we're going to end up with a clipped waveform on our output. So if we're too close to either side of our forward active mode, then our output waveform is going to be clipped. And so that brings up sort of the importance of why we want to have this Q point at a certain spot. So because we potentially are going to have our output being clipped or distorted, it's very important to be able to bias our transistor in the right space. So importance of biasing. So in the remainder of this unit, what we're going to do is we're going to focus on a couple different types of techniques for biasing our BJT. We're going to talk about pros and cons of the various techniques. Once we have a good handle on that, we're going to move into our next unit where we're going to focus more on using these BJTs as amplifiers. And so just as a final note here, if you want to see a figure of what a clipped waveform looks like, you can look on page 329 in the textbook, and it sort of shows this same example, but it has some different configurations for our Q point being too close to saturation, I believe is what it shows.